AP Chemisters, this is Mrs. Vandal bringing you Blankwalle video 7.2 number 2. When we left off on the first video, I said please watch this about Max Planck, and I really hope you did. I always find it interesting to find out where these things came from, okay? Anyway, go back, and if you remember the scene where Max Planck is thinking about, light and why don't metals disappear? You heat them up so high, and then he's watching the raindrops. Remember that? He came up with this idea, all right, about the idea of energy being quantized. Now, he was a theoretical physicist. He did not do any of the work himself, okay? So when he came up with this idea, he sent his buddies, who are true physicists, who worked in the lab, and said, here, go find the relationship between energy and frequency. Come back when you're done. All right, so do you remember this scene where those guys come to him and show him this really long piece of paper with all those zeros there? Well, how did they do that? Well, they took the relationship between energy and frequency. There you go. And they plotted it, okay? So the energy goes here, the frequency of the energy goes there, the frequency of the photon goes there. And what do you think they did? They found the slope, all right? They found that slope, and that was that really, really, really long scroll of paper with all those zeros on it. That's what this number is. So if I were to show you that, it would have 33 zeros after the decimal point, then the 6626, okay? And Planck, all right, was given the credit for that because he came up with the idea, and they called it Planck's constant. And I don't know why they call it H, but they do. All right, there's no H in his name. So anyway, being great graphers that we are, okay, let's put this in slope-intercept form. So y equals mx plus b. Well, my y is my energy, my m is my slope, which we said is Planck's constant, and x is frequency. Why did I not put a b in there? Because this line goes through the origin. B is 0, isn't it? So this gave way to this famous equation, E equals h nu, and that should be familiar from your first year chemistry, okay? So let's go to the next page. So using Planck's work on thermal radiation, 1905, Albert Einstein, let's pause for a second right here. I read an account where someone had asked Albert Einstein, in his opinion, who was the greatest scientist of all? Who was the most influential scientist for Albert Einstein? And he said it was Max Planck, all right? Can you imagine the honor given if Einstein said that you were the greatest scientist? Like, holy cow. So that should raise some eyebrows on what Max Planck did, okay? So based on the Planck's work, he proposed electromagnetic radiation was quantized. What does that mean? An exact amount, all right? These packets of energy in a sense, okay? In the same way equals h nu. So that, in a sense, gave way to E equals mc squared, doesn't it? All right. Can you see where there's maybe some relationships between what Max Planck did and what Albert Einstein got so famous on? All right. So how do we do this? Well, use the photoelectric effect. Don't forget about the photoelectric effect. You're going to have to remember that in chapter 9 when we talk about the PES of like it's called a photoelectron spectrum. So we use the photoelectric effect to kind of talk about that spectrum. So don't forget about this. So what happens? We bombard light on the surface of metal, and electrons are ejected. Now, what's so important about this? That if you have an exact amount of frequency, anything less than that frequency, remember how frequency and energy are directly related. So if there's anything less than that frequency of light, no photons are ejected. Okay, you have to have an exact amount of frequency before the photoelectric effect can occur, okay? So it's a photon, it's that particle light. So when the electrons are jumping back down into the nucleus after they're excited, they release that photon. And if that photon falls in the visible spectrum, we get to see it. If it doesn't, it may be, infrared, it could be UV, it could be something else, okay? And so here this became the energy of the photon is equal to h, Planck's constant, times frequency. And what can we do? We can substitute this frequency like, hey, what's new? C over lambda. All right, so we can substitute the frequency for C over lambda to get that equation. All right, so let's look at problem number 6. It says a nitrogen gas laser pulse with a wavelength of 337 nanometers contains 3.82 millijoules. That's a little m, millijoules of energy. So how many photons does it contain? Well, what do you think you ought to do first? Why don't you find the energy of one photon? All right, because that has the wavelength of 337 nanometers. If you can find the energy of one photon, you can find out how many photons you have. All right, so let's do this. All right, I'm going to use this same equation that we just had, equals hc over lambda. Why would I use that equation instead of equals h nu? Because what they give us? They gave us wavelength. All right. So let's see here. The energy of one photon is 6.626 times 10 to the negative 34th times c. Remember, c is a constant, divided by what? Well, what do I have to do with my 337 nanometers? I can't put nanometers in there. Well, why not? Because I have meters right here. All right, so I have to convert it to nanometers into meters. Do you remember what a nano is? A nano is 10 to the negative 9. Mrs. Vanderlei, why are you talking so funny? Because a nano is 10 to the negative 9. All right, so this is what I did here. So go ahead and pause this and calculate away and see if you got what I got. All right, this is what I got. Hopefully I didn't make a mistake, all right? But I'm not done with the problem yet, Mrs. Vanderlei. All right, what did the problem ask? How many photons are there? Go away. Now, does this equation make sense? E total equals how many photons you have times the energy of one photon. All right, hopefully that makes sense to you. So if I have a total of 3.82 millijoules, all right, notice I have a 10 to the negative 3, that's your millijoules, equals how many photons you have by what is the energy of one photon. And so when I did this, go ahead and divide yourself, see what you get. All right, this is what I got. All right, so 6.47 times 10 to the 15th photons, okay? Problem number 7 is very similar to number 6, so why don't you pause this and work it out, okay? And only when you are done with it, why don't you come back, all right? So see you in a little bit. Okie dokies. This is what I did. All right, I have E photon equals H nu. Therefore, I just started plugging in some numbers. Okay, and there you go. And then what did I get? I got E equals of one photon, 3.79 times 10 to the negative 19 joules. All right, that makes sense. All right, it's kind of in the range of visible light. Well, isn't that a good idea? Isn't that what a light bulb is supposed to do? All right. So anyway, let's go back and use the same equation. All right, and so now it radiates 100 joules. I didn't have to do anything weird. All right, per second actually, is equal to n, how many photons I have, times the energy of one photon, which I put over there. And therefore, I must have 2.64 times 10 to the 20th photons. Okay. All right, problem number 8, a little bit different. What happened? You are asked to solve for wavelength. So why don't you pause this, all right, and try to work it out yourself and then come back when you're done. Bye-bye. All right, I'm back. So how did you do? Well, I couldn't solve the energy of one photon first. I had to, well, actually I did, but I had to use this equation first, all right? They gave me the total numbers. This is 275 kilojoules, all right, of energy. And what else does it say? What wavelength is sufficient energy per photon? Well, this would be per hopefully 1 mole is how I interpret that. Why? Because of this. This is kilojoules per mole. So if I have 1 mole, then that's how much energy I have. So that's my energy of one photon. If you got stuck, all right, because you didn't know what n was, why don't you pause this and then finish out the rest of the problem? If you figure that out, then keep going, all right? So I'll pause this, let people catch up, and then I'll be right back. All right, so this is my energy of one photon, okay? And now it's just a matter of plugging in this equation again and solving for wavelength, okay? So here is my energy is equal to Hc, I'm running out of room, over lambda. And so if I multiply both sides by lambda and divide by 4 point whatever, and then I get this. Okay. So problem number 9 is actually, I think, the easiest problem. So why don't you go ahead and solve for this yourself? Pause this and come right back. Okay, welcome back. It was really a one-step deal here, all right? So I'm just using this. They are telling me the wavelength. They're just asking me what's the energy, all right? You don't have to do anything weird. So here's this, HC. Notice I'm always using the same numbers each time. Why? Because they're constants. All right, and I use the 450 nanometers, and I did my math, and there I go. Oh, let me just pause for a second. Let me go back up here again. I hope everyone can make this conversion here. How do I do that? I multiplied by 10 to the ninth. Nanometers equals 1 meter. So if I multiply this by 10 to the ninth, I got 435. Okay, I just didn't know if you saw that. Let's go to the last page, then we're done. All right, it says the light of 3 different waves. You have 325 nanometers, 455, and 632 is shined on a metal surface. The observations for each wavelength A, B, C are as followed. A, B, and C. A has no photoelectrons or observed. That's a key word. Were observed. Photoelectrons with the kinetic energy of that were observed, and photoelectrons with kinetic energy of 51 kilojoules per mole were observed. Which observation corresponds to which wavelength? I'm hoping that observation A is a no-brainer. What do you think it is? Go ahead and jot down your ideas. Well, I said A was 325. Why? It's out of the visible range. All right, what is the visible range? Between 400 and 700. Okay, so now I'm down between B and C, the 155 and the 51, and I got these two. Okay, so which would be which? All right. Well, here's a very important observation. What happens when, let's say, as energy goes up, what happens to wavelength? Wavelength goes down. All right. So I wrote as wavelength decreases, frequency and energy increases. So this has the greater energy that must have the lower wavelength. And that does make sense because that's probably in the violet range, and violet has the greater amount of energy. Think about this, which has more energy, ultraviolet or visible light? What's going to do the damage when you have a suntan, all right? It's the UV breaks the bonds and causes your skin to change, all right? It has enough energy to do that. Visible light alone, you don't get a suntan just being under a regular light, do you? No, you don't. All right, so what's left? I said letter C is your larger wavelength, because as a wavelength increases, both frequency and energy decreases. All right, so I hope this was helpful, and Makes sense. I hope it reminded you of things you learned from the first year of chemistry. So I'm done. Don't wait to be great. We'll see you next time. Bye bye.